Professor Kriti, are ready?
Yes, sir.
Amish sir, ready. You can go ahead.
Yes, we can start with the ma'am.
Okay. So, sir, shall I begin?
Yeah, go ahead.
May we start, Professor Wang and Mike?
Yeah, I'm good.
Yes.
Yes, I'd be happy to start. Welcome, everyone. Thank you for joining today's seminar. I'd like to welcome you all. And it's my honor to be here. It's my honor to introduce our guest speaker for today. So welcome to one of several of our joint seminar series. I'm Michael Tastani from Binghamton University. So on behalf of Binghamton University, our Dean, Dean Srihari, I want to thank you all for being here. I want to thank the advisors and coordinators for this event, certainly Provost Nile. We appreciate all his support in this collaboration, and we look forward to our future collaborations with Dr. Amarish, who's been great to work with, Professor Kriti, Professor Dinesh have all been wonderful to work with. And we're all here because of their hard work. So thank you so much for that. Want to just make you all aware of our upcoming events. Of course, we have Dr. Wong, who will be giving us a talk on autonomous systems today. I think you'll really enjoy it. He's targeted at from a student perspective. So I think students will be able to see themselves in this research. But we have several great upcoming talks as well, where we'll have some outstanding thought leaders from both NUV and BU. So, very excited for our upcoming events as well. And without further ado, I want to turn the floor over to my colleague, Dr. Wong. He's going to give a talk today on autonomous systems. You can read his very deep and diverse background here in energy and mechanical systems. And of course, now he's a professor in our industrial and systems engineering department, doing some great work there. He's an outstanding teacher. I can tell you that firsthand, seeing his classes. And he's doing some great research. His focus is on design, modeling, management of complex systems in various domains like healthcare, like energy, like manufacturing. And his research is focused on making those systems more efficient, more reliable, more cost-effective, and more sustainable, right? And all that means the most efficient use of time, space, people, money, information, equipment, and materials, etc. So an expert in all these areas, and I think you're really going to enjoy his talk today. So without further ado, Dr. Wong, I'll turn it over to you. Thank you so much.
Sure. Thank you, Mike. I'll start to share
Okay.
my.
Hello, everyone. I, Kriti Vishesh Jaiswal, working at Navrashna University, Baroda as an assistant professor in the School of Engineering and Technology. I welcome you all to the webinar series organized by School of Engineering and Technology, Navrashna University, jointly with Thomas J. Watson College of Engineering and Applied Science, Binghamton University, USA. Navrashna University is a conglomeration of 5 schools and is established in the year 2009 with the vision to offer quality education. The School of Engineering and Technology was established in the 2012 with the vision to become one of the best schools of excellence in technical education and research that meets the global standards. To continue with this vision, the school regularly organizes workshops, seminars, webinars, and FDPs for the benefit of students and the society. As a part of these initiatives, School of Engineering and Technology, Navrashna University, and Thomas J. Watson College of Engineering and Applied Science, Binghamton University, USA, have collaborated to offer various programs with academic orientation, which span in several areas such as joint seminar series, joint certification programs, faculty development programs, faculty and student exchange programs, summer schools, joint research, and joint conferences. The first event in this collaboration activity is NUV BU Joint Seminar Series. Now moving further, I would like to It's my privilege to invite Dr. Nile Yachnik, Provost, Navrachna University, to enlighten us on more about this collaboration.
Thank you, Kriti. Welcome to the Navrachna University and the Thomas J. Watson School of Engineering, Binghamton University joint seminar on autonomous systems. And as Kriti said, this is the second seminar that we have organized as a part of our ongoing collaboration. The collaboration is a very deep collaboration which covers several areas: teaching, research, faculty exchange, student exchange, projects, conferences. There are several things which are planned. And today, Professor Wang will be speaking to all of us on autonomous systems. And I welcome all of you. I wish to thank Dean Srihari of the Thomas J. Watson School, Binghamton University. Thanks to Professor Michael Testani. And also thanks to Professor Wang for spending your time with all of us today. We look forward to your session. Thank you.
Thank you, Dr. Nile, sir, for sharing this information about this collaboration. So today is the second webinar of this NUV BU collaboration webinar series. And the webinar is titled Autonomous System, presented by Professor Yong. The autonomous vehicles have quickly grown in numbers and popularity. And this webinar describes a case study of a computer vision-based autonomous vehicle system for warehouse materials distribution application. So I request Mr. Michael V. Testani, Director of Industrial Outreach, Thomas J. Watson College of Engineering and Applied Science, Binghamton University, to shed some more light on today's event.
Yes, thank you, Kriti. And again, thank you for having us here today. We're delighted to be here. We're delighted to be part of today's collaboration, as well as taking this journey with you down the road of future collaboration. So thank you so much for having us. Certainly appreciate all the good work from all the leaders there at NUV. So thank you so much. And as I mentioned earlier, Professor Wong is doing some great research in a lot of different domains. I think you're really going to enjoy today's talk. He's going to get into hardware systems, software systems, algorithms for autonomous systems. So I think his talk, really appeals to many disciplines, not only industrial and systems engineers, but computer scientists. I think you can see yourself in this research, mechanical, electrical engineers. You can all see yourself in this research. And I think you all have a bright future, if you so choose, in the area of autonomous systems. All right. So without further ado, I wanted to turn the floor over to my colleague, Dr. Yong Wong. Dr. Wong,
Okay,
over to you.
thank you, everyone. I'll start to share my computer screen. I also temporarily turn off my camera for now. I'll turn that back on after the presentation, the question and answer session, just to save some bandwidth, because I noticed some little bit disconnection when I share the video at the same time with slides previously. So can everybody see my computer screen right now?
Yeah.
Yes.
Okay, so the topic is computer vision aided autonomous navigation system using an overhead camera and the Raspberry Pis. So this is the outline of the talk. I will thank everybody who have contributed to this project, and also give you a brief introduction about the project, and also I'll briefly introduce about the hardware and software system we have been using for this system, and then how to connect this hardware and make it work, make it communicate. And next would be the autonomous navigation system to give it intelligence so it can navigate by itself. And finally, there will be conclusion and potential future work and some of the lessons learned from this project. So first of all, I would like to thank Watson Institute for System Excellence. So this is another independent institute under Watson College. Dean Srihari is also the founder of the WISE, Watson Institute for System Excellence. And I would also like to thank System Science in the Industrial Engineering Department, Dr. Kasane, who is the chair of this department. I'm also affiliated with the department. And Dr. Kazami is also the director of WISE currently. This project is funded one master student, Chen Xiu Ai. She was doing the master degree last year for about 2 years. She graduated last summer, and this is a part of her work. She was financially sponsored by WISE and the SSIE department. At SSIE department, we have 2 options for master student to choose. They can either develop a thesis and defend the thesis and graduate, or they can choose to do a termination project. Finish the project, they can also graduate. So this is the termination project pathway. Last but not least, I would like to thank the Navrachna University, the leadership, the top management, and everybody who is here attending this seminar. I really appreciate your time, and it's really my honor, my pleasure to be here to talk to the faculty members and the students. So when people talk about autonomous systems, they may think about the autonomous cars, but autonomous systems may have a much broader definition than just self-driving cars or autonomous cars. There are also robots. Robots can also be considered as autonomous systems. There are also flying drones. These drones can also be assigned with artificial intelligence, so they can also do the jobs autonomously. There are also underwater autonomous system. They can patrol the sea in the sea underwater for certain tasks without too much involvement of human beings. So in today's talk, I'll just showcase some system we have developed over last year using a computer vision-based system to autonomously navigate a small vehicle, a Robocar, for indoor environments. So this can be potentially used in many applications, like in hospitals, supermarkets, airports, classrooms, restaurants. So it can also be used for warehouse material distribution. For example, if you have some small package you want to deliver from one location to another location, you can just assign these robots to do the job autonomously. So as I mentioned, this is a termination project. Usually I just assign the project and give the specific objectives to the students. Then it's up to the students to do the study and research, find the reputable sources to collect the data, collect the information, and then compile the code by the hardware and integrate the software together so they can actually function as the entire system. We do have a very small fund to fund the student to purchase the hardware. It's usually about $200, $300. And these are the specific objectives I proposed to the student. So the first objective is that the system should be able to identify the vehicle, which is the Robocar, and other obstacles in real time through an overhead camera. So other obstacles, if you think about the warehouse situation, it could be people who are moving around. It could be shelves, it could be totes, it could be boxes, it could be conveyor lines or machines, anything you can think of that could appear in a warehouse situation. So there's some static objects and some moving objects. And plan and track the optimal paths for the Robocar or vehicle on the ground. So we try to find the best or shortest paths from one place to another place, considering this background. So the vehicle can actually move from the starting point to the destination. And then we have the communication system. This communication should be done wirelessly. From the overhead system and ground system. We have 2 systems connected together. Overhead system, we have a camera, and ground system, we have the vehicle that is actually moving. Then we try to navigate the system to move from one point to another point while avoiding hitting any of these obstacles on the ground. After that, we do not want to rely on too much of the landmarks or other sensors. We just want to use one sensor to see whether this can be done or not. If this can be done, then we can gradually add more sensors to make it more reliable, more resilient, more robust in the future. And we want to build low-cost prototype from scratch. So we, because we only have like a $200, $300 budget for the student, they can purchase hardware from eBay or from Amazon. And after they got the hardware, they can do the connection and make the things work. So this is another requirement for the student. After the student received these requirements, she started to work, and this is a design she came out with. We have a camera that is mounted on the ceiling. It is connected with the Raspberry Pi board. It will process the video and try to identify whether this is a box, this is a moving person, this is a cart, this is a Robocar. And we can set the starting position and also the final destination on the map. And it will try to plan the best path from the starting point to the final destination. After this path is planned, it will transfer that path wirelessly to a ground system. The ground system also have another Raspberry Pi. It will accept the waypoints that has been planned, and then it will try to use the driver to control the Robocar, which will move from the starting point to the final destination. So this is a basic design of the hardware system. Now, in terms of the functionality design, she came up with this diagram. So first of all, the overhead camera, we just do the job of capturing the video on the scene. And then it will transfer the video to the Raspberry Pi board mounted on ceiling as well. So this Raspberry Pi will process the video information, try to identify different type of objects, and then try to get a good sense of where the Robocar is located, where its surrounding objects are located. Try to map out the entire environment. Based on that information, you will try to plan the best path from one place to another place. Of course, this part should be done in real time because the object can be moving. So this path planning part should be done in real time. It should be updated every millisecond or every seconds to keep the information updated. So the best path information will be transferred wirelessly to the ground Raspberry Pi. So this ground Raspberry Pi will receive the information and try to keep track of whether the Robocar is actually on track or not. It would control the motor to move left to right, forward, backward, moving forward and stop and things like that. So finally, the ground robot will just follow the path that was planned to move to the final destination. So this is a methodology or the functionality design of the entire system. In terms of the function, in terms of the hardware, so for the overhead camera, because we don't have very limited budget, we just try to buy something, some hardware to make a prototype system. This is not meant to be used actually in our warehouse. Actually, during the COVID-19 last year, nobody is allowed to come to the lab or go to the manufacturer to do the experiments. So the student just developed the entire system in her apartment using very inexpensive materials. So this is the camera. I'll show you the specifications of this camera and Raspberry Pi information. So this is the camera, very cheap one. And we have the Raspberry Pi for overhead system. We have another one for the ground system. These two Raspberry Pi are basically the same. The only difference is that some of the software that was installed here for video processing, it was not installed here. So it's not necessary for the first phase design or first phase development. Later, we probably also need to install the artificial intelligence video processing software on the ground system if we decide to implement the ground vision as well. That is for a second phase consideration. Then we have the drive board. this drive board will just do the control of the wheels or servos and try to make sure the ground Robocar will move left to right and follow the path for the waypoints. That was planned. So basically, this is a hardware design. Of course, the entire system will be operating in a wireless environment. We assume the router and other network infrastructure had already been there. So we don't have to propose any budget or hardware for that. We just assume that is already there. So this is a specification of the camera system. You can see that this is a camera, actual camera. This is a size. It's very small, just like a little bigger than a fingernail. This is a top, and also the other side of the cable can be connected to the Raspberry Pi. It has a very good picture resolution and video resolution. This can be like a 1080p high definition, but during our application, actually, we don't need so high resolution. Actually, the Raspberry Pi is not so fast to process 1080p. So we have to reduce the resolution to about 800 times 600, that kind of pixel. Otherwise, the Raspberry Pi will be very, very slow. And then we have the angle of view, field of focus. These are specifications for this camera. Of course, when we try to implement this one, we try to just develop the prototype. As I mentioned during COVID-19, our focus is not to implement this one in a warehouse. Also, the frame per second, this is how fast the camera can capture 30 frames per second. This one is also too high for our prototype development because the Raspberry Pi is not so powerful to process this frequency. So we have decided to reduce that to about 5 frames per second for our specific application. So this is a camera system. This is what the Raspberry Pi looks like. This is a Pi board with GPIO pins. Pi 3B has about 40 GPIO pins. These are pins that we can control the voltage to be high and low. So it can input the sensor information or output some signal, so we can control the servo motors. We have the network cable Ethernet connection here. We actually used the wireless, so we didn't actually use this Ethernet. We also have the keyboard. I think it has 4 USB cables, 4 USB ports here. We can plug in keyboards, mouse if you want, and the sound. This can be plugged into a speaker, and we have the camera port will be plugged into this port. It can support dual monitors, and also the power can be directly connected to this one to power on the Raspberry Pi board. The other side, we have a SD card slot, so we can slip in the SD card for all the software. It will be operating on this SD card. So the cost of this system is about $40, and also we have a SD card which is about $8. And we actually have a sensor kit before we start this project. This sensor kit was for undergraduate course computer programming for engineers. So we have that one for students to actually play around and trying to understand different type of sensors for hardware programming using Python and Raspberry Pi. So we have vibration sensors, we have temperature sensors, moisture sensors, motion sensors, and also many other different type of sensors. So this is just for the student to understand how this entire system works, how to do the programming of these GPIO pins to get better understanding, because the student doesn't have too much background of hardware programming. This step is optional for a student who already get very good understanding of hardware programming like Raspberry Pi. At that time, we try to make sure the student understand everything. So this is a step that was necessary. After that, we have to install software in the system. So we have the operating system that has to be running in the background in the SD card. So this is after installation, what it may look like. And also we have to install Pi 3.7. This is the older version at that time, 1 year ago. Now I think it's 3.8 or 3.9 is already out. We connected the system using virtual desktop because we find it's more convenient to do the debugging and programming in that way instead of directly connect a computer or keyboard to the Pi. So we just need the IP address of the Pi and connect that through VNC. For the communication between the overhead system and the ground system, we use a protocol called message queuing telemetry transport, or short for MQTT. Other people just refer to it as Mosquito. So this one is very popular communication protocol in Internet of Things programming. It is lightweight, doesn't consume a lot of power. It can be using publish and subscribe this kind of a network protocol. It can be supporting multiple devices and communication at the same time. So this is very convenient. We just implement this one on the Pi boards for both ground system and overhead system. For the overhead system, overhead Pi board, we also install the video processing packages and artificial intelligence packages. The first one is OpenCV. It is used to process the videos. TensorFlow is used to identify different type of objects and try to use that information to find the coordinates in the ground and try to map out the entire environment. And their collaborative use will be able to locate different objects and also provide us very accurate information about waypoints we're going to plan for the Robocar on the ground to pass through. I want to mention that OpenCV is, they only have source code. When you try to install this one on the Robocar for the overhead system, it takes a very long time. The first try was not successful. I think the student have to try that 3 times for it to be installed, finally installed. It will take like 6 hours for the compilation of this OpenCV package. The software are all free. Here, this is another piece of hardware. It's called drive board. This one we're trying to use this one to control the servo motion to make sure the servos will turn forward, backwards to control the wheel movement left to right and forward, backward. It also is equipped with IR sensor and ultrasonic interface. That means it can do the detection of infrared or even equip that with night vision. We didn't use this functionality at the time, but of course in the future, we can also give it such functionality for the system. It can be connected to the power supply. There is a battery that is mounted on the Robocar. It can connect the drive board directly. So it will be powered through this lithium-ion battery mounted on the Robocar. So this one is the most expensive piece for this entire system. It's about $100. This Robocar, the size is just about the shoebox. And also it's not very heavy. It's less than 1 kilogram. And the lithium-ion battery can power the system to run for about half an hour. And we just use the wireless communication because everything should be done using Wi-Fi. It has that capability. It can communicate the signal up to 80 meters. But if you have the blocks like walls or shelves or people standing in front of that, the distance can be greatly reduced. But for our prototype development, we just try to demonstrate whether this system will work or not. So the environment was actually in her apartment. So this is not a big concern. Of course, it has servo motors and chassis and wheels. So this will be necessary for the control. to move from one location to another location. After we purchase the hardware pieces, we have to connect them together. Of course, we already installed the software on these Raspberry Pis. Here you can see that the camera is directly connected to the Raspberry Pi port. And also we have some other connection like the power, the monitor, the mouse and keyboard. We can also use the USB drive to input and output data or do the programming if we want. So this is connection for the overhead system. So this entire system will be mounted in a very high location like a ceiling. Then we have the connection for the ground system. This is a drive board. It is connected to the Raspberry Pi. And the drive board will also have a cable that is go to the lithium-ion battery. So it will power the entire system on the ground. After cleaning up the wires and try to tidy up the entire system, this is what it looks like. For the communication of the overhead system and ground system, as I mentioned, we use a MQTT protocol. So this protocol will require the IP address of the Raspberry Pi on the overhead and also the Raspberry Pi for the ground. So depending on your network, you can have different IP address. So this is just IP address we have been using during the development. MQTT will require two pieces of information. One is the topic of the message. Another one is actually the payload. The topic is the path information we have sent. And also the payload in this testing is just the waypoints. That means X, Y coordinates the Robocar has to pass. So we have tested using some random X, Y coordinates information and directly send that to the receiver, which is the ground Robocar Raspberry Pi system. So it seems like the communication is correct. The delay is very, very minimal in this case. And we also try to control the Robocar movement through the programming of these GPIO pins to give it high voltage or low voltage of these 4 different pins. Depending on the high and low voltages, the car will move forward, backward, left, right, and also brake. There is also a small camera mounted on the system. In the first phase development, we haven't implemented the functionality for the vision. But in the second phase, we're planning to implement this ground vision as well. So at this stage, the system is controlled by the student. There's no intelligence. It cannot move by itself. It has to be controlled by a person. Now goes to the next phase, which is autonomous navigation phase. So for this phase, we have to go through 5 different sub-steps: image or video processing, localization and mapping, path planning, and then path tracking. I'll introduce these sub-phases one by one. So for image processing, the final goal is try to identify different objects on the ground. And we try to have a very high accuracy. Otherwise, you may miss some objects on the ground. That will be a very bad situation. You may actually hit those obstacles if the car is trying to move through those obstacles. The first method we tried is using OpenCV contour recognition. We tried these specific functions like canny edge and contour discovery, going through 5 different steps, like pre-processing, binarize the images, and try to detect the edges, and contour recognition, and finally, I try to identify the target objects. But you can see that it can only identify 50% of these objects on the ground. We have a black case, we have a gray case. This is a white plastic box. This is, I think this is a coffee mug. After going through these steps, you can see we can correctly identify this one and this one, but the other 2 have been missed. The reason is that at the time we have to put a lot of A4 sized white paper on the ground. You can see that when we try to glue them together, we have some kind of overlapping. These overlaps can interfere with the white box, which is on the ground. You may think this is just some edges, or this is also the background. It's not an object. So as a result, this white box was not detected. Due to this pattern, it can create problems, and also due to the shade, the shadow. You can see the coffee mug have some shadow. There's also some uneven lighting conditions in this area, so it was not detected. The trial results show that this is not a good way to do the detection. Then we switch our gear and try to go through another path. This one is trying to use a TensorFlow to do the detection of the objects on the ground. This one just to show you the basic idea of how TensorFlow artificial intelligence works. And if you have many different objects, you can use these objects to train the algorithm, trying to identify different features or different patterns of different obstacles. So this one is showing, for example, if you are developing an algorithm, try to identify different type of vehicles, like a sedan, Jeep or SUV, we have some motorcycles, we have the Robocar. We can give very large data set into the algorithm. The algorithm will automatically, using deep learning, identify different features or patterns. After that, it will try to build weights and the biases in the network. And if you have new data input, it will try to extract the similar feature and try to input that into the network and try to identify whether this is a real Robocar or this is some other vehicles. For warehouse situation, you can train different type of data. It doesn't have to be cars. It can be people, it can be shelves, it can be totes, it can be conveyor lines, it can be some other objects that may appear frequently on the floor of a warehouse. So you have to change this part and do the training by yourself. So at the time, as I mentioned, the student was in her apartment. Everybody is not allowed. There's a lockdown. Nobody is allowed to go outside except for grocery or something. So she took about hundreds of pictures of these Robocars in different lighting condition, different background, with single or even multiple objects. And so this one is example. It's showing the Robocar is on the ground, on the floor with multiple other objects. We have another picture of the Robocar on the table. Robocar is on the carpet. Robocar is on chair. So the key point is that we have to mix different kind of background, different kind of lighting condition, and number of objects. We have to reduce, as I mentioned, the video can be 1080p, but it will be very, very slow for the Raspberry to process the large file size. We have to reduce that to 800 by 600, and also reduce the color image, RGB image, to black and white for faster processing. After we collect the photos or videos, we try to use a tool called label image to identify and different type of objects and their bounding region. So this one is, for example, from here to here, we have X, Y information on the top left corner, X, Y information of the bottom right corner that will bound the region that contains this box. This is a bigger box. This is a small box. This is a Robocar. You have to do that for all the objects that is of interest and try to save that information in the computer file. And later that computer file will be used for training and testing. As mentioned here, we have hundreds of these images. We split them into training part, which is 80%, and testing part, which is another 20%. Then we have to create the training profile, like how many different type of classes, objects are there in the training data. At that time, the student just tried 3 different types. Of course, in a real warehouse situation, you may have to identify different, maybe there could be dozens or maybe even hundreds of different type of objects. That means your training data set must be much higher, much bigger than this one. And we have to specify where these training and testing data are located in the computer, inside the computer. So we can find those information and use the information to do the training and testing. The algorithm the student was using was called faster RCNN. Actually, later we find out maybe YOLO 3 or even YOLO 4 could be a better algorithm. But at that time, the student was using faster RCNN. This is the tensor board output. It shows the loss function or the errors. We try to basically minimize the error. It will never go to 0. After a certain amount of iterations, she just stopped the training. So this is about 25,000 training iterations. Then the algorithm is stopped. After sufficient training, we start to test on new images on those 20% for testing. So these are new images the training data never, training algorithm didn't see. After the testing output showed that we can very confidently identify different type of objects with very high confidence levels, like 99%, 98%. Can also identify different objects, multiple objects in the same scene. And if they're having some kind of overlapping, you can also identify those objects. So for this one, like this fruit, you can also train if you want, like the bananas, but it's not relevant in our prototype design. But of course, if you have more time, you can do that. I would say the image processing training phase is very time consuming. If you have very large data set, thousands of images, or even millions of images, you have to do the labeling by yourself, or it will be very time consuming. There are also some services that can provide the semi-auto labeling. So that means it can greatly reduce the labeling time for you, but you have to pay for the service. Next phase will be the localization and mapping. Here, again, we're trying to use TensorFlow to identify the location of this X or information, Y information, and the bounding box, and try to identify which type of this obstacle is. Like Robocar is here. We have the big box, we have the small box. So there information. After we get the coordinates information, we'll try to map out the environment. Like the Robocar is located here. We represent that as a red dot, and we have the bounding boxes. These will be marked as black. These are prohibited areas. We cannot go through these areas. We also have to make sure that the size of the Robocar is enough for passing through this kind of region. So we have several different type of setup. This is a setup with 2 boxes that are very far away from each other. This is a setup for 2 boxes are close to each other. They can correctly identify this information and try to map out the environment. Based on the environment mapping, we can create the shortest path from one point to another point. The basic idea is try to find the shortest or fastest path from the starting point to the final destination. We tried 2 different algorithms, Dijkstra and A*. Dijkstra algorithm is just like when you throw a stone into a lake, you can see the waterfront moving in all directions in equal speed. So finally, it will reach to that final destination. And after it gets here, it will try to mark the shortest path in the memory. So this will be the best path for this kind of Dijkstra algorithm. The problem with this algorithm is it's very slow. So Later, the student also tried A-star algorithm. It has some bias towards the most promising direction, so it will move towards that direction in a much faster speed. And turns out this one is better when we did the testing. So this is the prohibited areas. We try to find the path from one location to another location, and this one will take longer. A-star will take much shorter time. Next step will be to do the control to make sure the vehicle is moving on the path we have planned from one place to another place. And we tried the PID control for model-free based steering control. We also tried pure pursuit control for model-based steering control. It turns out the model-based steering control method is a little bit better than model-free steering control. Due to the limitation of the Robocar we purchased, it's low cost. It cannot be separately controlling the different wheel. We can only control all the wheel at the same time. So there's no separate control. Otherwise, we can also try like a front wheel control or rear wheel control or some other more advanced algorithms. So we have to do the simulation first before we do the experiments. This is just showing you two boxes on lane like this. And we try to plan from the starting point to the final destination. These little crosses are the waypoints that was found based on the past planning. This is just experiments. The car is moving from this direction horizontally and move away to that other direction, finally, the final destination. So this is one setup for the experiment. We have done another one. Two boxes are very close to each other. And this is the simulated results. The path will be going through the waypoints. And this is simulation. This is experiments. You can see that it's going horizontally and then turn and go inside to that direction. So at this stage, the vehicle is moving by itself, controlled by the information from the overhead camera and also the algorithm. And also following the best path. Student is not controlling the vehicle. So this is a summary of the progress of the system. We have built the hardware and also connected that with the software to give it intelligence so it can autonomously navigate from one point to another point. This system is not perfect. We've been running into several problems during the development of this system. The first one is due to the connection of these wires and GPL pins, it was just loosely connected. During the movement, there was some vibration. You can see that there's a short circuit, and smoke came out, and the result is the wire burned. And also, it also burned the dry board. And we tried to buy the same dry board, but during COVID-19, it was out of stock. We have to buy a different type. So that is why you see in this video, we have to have a cable. Otherwise, we don't have to need this cable. We can directly connect to the lithium-ion battery here. So another thing we're planning to do is try to give it ground vision. We have experienced some disconnection or internet problems because the wireless connection is not always 100% reliable. Sometimes when the connection is lost, the Robocar just stopped there. So we try to give it ground vision so we can also rely on the ground vision if there's no connection wirelessly. So we can more safely navigate from one place to another place. We tried this one using OpenCV edge detection algorithm. Seems like this is very promising. It can detect the objects like the red bar, that means where the objects are, the distance. This is just some toy cars in her apartments. She did the testing. But of course, in some other location, it's not so perfect. Like there are still some noises we try to eliminate in the future development. And another further development could be install multiple cameras and connect everything in a grid, so you can cover a much wider area in a warehouse. Think about a bigger warehouse. You have many shelves. or the toe shelves can block the vision of the ground of the overhead camera. But if the Robocar is moving to the other area, the other camera can pick it up, and then it can continue to move. So it can relay the movement using multiple cameras. It can provide more redundancy, more reliability for this application. So it can have many different type of applications in, as I mentioned, in warehouses, in hospitals, in airports, in classrooms. It can also be used in supermarkets. I think this type of robot is already out there. Walmart has used some of these cleaning robots in their supermarket stores. I think they're just following a schedule, like in the morning or in the evening, they just send out the robot to do the cleaning of the entire floor, entire market. Just imagine if the camera, they identify some customer drop a bottle of wine, it's a mess here, it can directly send out the signals. The robot can come here, do the cleanup and go back to the dock. So this is some potential application of this navigation system. I think that's all the information I want to show. Lastly, I have a short video. Let me show you this video. This is about the Binghamton University. Some of the short video to introduce the university.
Dr. Wong, if this video has an
This
audio,
is a place where bright.
Yep.
audio is coming. Yeah, go ahead, sir. Go ahead.
Okay, sure.
This is a place where bright minds meet. A world-class institution with renowned faculty, endless opportunity outside the classroom, and a tight-knit community. This is Binghamton University, the premier public university. Binghamton is located on a stunning 930-acre campus, nestled in the wooded hillsides of upstate New York. People at Binghamton affectionately refer to the campus as the Brain, a reference to the university's unique layout. But it's not just a neat nickname, it's a constant reminder of our pursuit of knowledge and understanding. And at our 7 different colleges, that pursuit of knowledge is tailored to each student's personal passions. Follow the green paw prints and you'll end up at the state-of-the-art admission center, a one-stop shop for students. More than 30,000 applications make their way through the center's doors. Put simply, an acceptance letter from Binghamton is something to be immensely proud of. Binghamton University is a home for living and learning. More than 7,600 students reside in the 6 residential communities that outline campus. Ask any student which residential community they live in, and they'll likely well up with pride. Community is key at Binghamton University, and each residential community offers a unique and enriching living experience, one that enhances the academic experience and reinforces an atmosphere of camaraderie. Career development, mouth-watering food, bowling, billiards, and more. The University Union has it all. The Union is a center of information and entertainment for Binghamton's student body. Binghamton University offers an incredibly diverse range of classes, from film theory to tree climbing to the physics of materials and everything in between. You'll find these classes spread out over campus with traditional classrooms, ultra-modern laboratories, and even classes in the great outdoors. Research is big at Binghamton, and the Innovative Technologies Complex is the university's research hub. Here, leading scholars work together with student researchers to push technology to astonishing new levels. From stunning visual art to stirring theatrical performances, our school supports a strong community of artists working in a variety of media, fostering artistic growth and offering year-round enrichment and entertainment. You'll see plenty of Pantone 342, the university's official color, when you come to campus. We have a proud tradition of supporting athletics at Binghamton, and with 21 Division I sports teams and a devoted student fan club, there are opportunities for athletes and spectators alike. Do Kung Fu, badminton, or Ultimate Frisbee sound like fun? These are just a few of the 40 or so club sports Binghamton students get to choose from. Students also have access to FitSpace, a 10,000 square foot fitness center where swimming, fitness classes, and new equipment make staying in shape no problem. Within our campus lies a 190-acre nature preserve featuring a 6-acre pond and trails for biking, running, and hiking. A hotbed of biodiversity, this space also offers real-world research opportunities. The University Downtown Center, located in the heart of downtown Binghamton, is home to the College of Community and Public Affairs. Through professional research, civic engagement, and public service, students here find a practical way to change the world. With a beautiful and bustling campus, incredible research opportunities, a spirited and diverse community, and a continual commitment to excellence, Binghamton University is truly the premier public university.
Yeah, that's it. Thank you, everyone.
Thank you, Dr. Wong,
Thank you.
for sharing your valuable opinions, findings, and knowledge with us today. Now, session is open for questions and answers.
Yes, what questions do participants have? You could type in the chat or raise your hand and whatever you'd prefer.
Hello.
Hi.
Yeah. Hello, everyone. Hello, Professor.
Yeah, hi,
This
how are
is. How are you? Fine. I'm fine. Good. My name is Jai Mehta. I'm from Navrachna University, CSC Department, Computer Science and Engineering. Firstly, I would like to thank you for sharing your experience regarding autonomous system, and it was really very wonderful journey we had just now. My question is, which are the security parameters which we need to take care or we need to consider as far as the wireless autonomous system or wireless autonomous vehicle is concerned? So please guide me in this.
Yeah, that's a very good question. Our department is called the System Science Industrial Engineering Department. So our main focus is try to put things together and try to make sure it works. And then in terms of cybersecurity and things like that, I think definitely we need to collaborate with computer science department in that respect. It is a very valid concern that wireless communication probably is not as secure as wired communication. But I think there are also some measure you can probably do to make this entire system more secure. At this stage, we are trying to develop a prototype. Of course, in the future, we are also trying to integrate more secure communication capability of the system. I think maybe we can hire you as an expert. You have that knowledge. We can work with you. This is kind of a collaboration. Yeah, that is a very interesting question and also very valid question, valid concern. Yeah.
Yeah. Thank you. Thank you so much, sir.
Yeah.
Any other questions? We probably got time for maybe a question, a couple of short ones. I know we do have to get Dr. Wong to his class here in a few minutes. He's teaching.
Yeah, yes, sir. Yes, sir.
Yeah.
But we do have time for maybe one more question.
Quick question.
Yeah, I'm Sneha, and I have a question that as sir told about TensorFlow, the whole working of TensorFlow. So I just wanted to know that suppose in TensorFlow, we are having any techniques or we are having any methods if any overfitting situation occurs in the entire TensorFlow process. So do we have any methods or techniques to overcome that overfitting process?
Yeah, I think some experts in this area, they say that in order to recognize one type of obstacles or objects, you have to use about 2,000 samples to do the training. So if you have, let's say, 10 different objects, 10 different type of objects, you have to use 10 times 2,000. That means 20,000. So I think the only way right now, a lot of people are pursuing this direction is that they try to increase the size of the sample.
Okay.
Overfitting could be a very annoying problem or concern. But I think if you can increase your data size, sometimes it's very easy, sometimes it's not so easy to increase your sample size, of course. That could still be a challenge in this autonomous vehicle, autonomous system research field.
Okay. Okay, sir. Thank you.
Yeah.
Thank you, sir.
Yeah.
Professor Wang, there is one question in the chat box from Mr. Chirag. He's saying, can we use front camera and image processing embedded on Robocar instead of using in overhead systems and use Bluetooth signals to navigate to goal?
Yeah, yeah. I think that is what we're planning to do in the second phase. In the first phase, we just try to use overhead system. It could be a little bit delayed. And if you have the ground system, ground vision mounted on the Robocar, that can probably more reliably guide the navigation. And in some cases, it could be in more real time with much less delay. We can even apply some other sensor, not only just the cameras or visual sensor. It can be ultrasonic sensors. It could be even lighter, but it'll be more expensive. Of course, it can be increasing the capability of the system.
Thank you.
Thank you, Dr. Wong.
Yeah, thank you, Mike. I think maybe you
have to get Dr. Wong to class. Go
Right.
ahead, I'm sorry.
Thank
I
you
think
so
you-
much, Dr. Wong. Thank you so
Yeah.
much.
It's
And
my
if there are
great
any
pleasure to
questions,
be here.
we'll route them to Mike.
Yeah, yeah.
Yes, any other questions, please send them to me. I'll get them to the professor and he'll be happy to answer them.
Right, right.
Thank you. Yeah, so thank you, Dr. Wong. Appreciate this. Provost Nile, Marish, Kriti, Dinesh, all the students and faculty who came today. Thank you so much. A pleasure, honor to be here for sure. Thank you.
Thank you.
Thank you,
Thank you so
everyone.
much, sir.
Take care. Thank you.
So-
Thank you very much.
So now I would like to invite Dr. Amrish Bhatgujar, Head School of Engineering and Technology, Navrashna University, for concluding remarks. Over to you, sir.
Thank you, Ms. Kriti, and thank you very much, Dr. Yong Wong, for your detailed talk, wonderful discussion on the topic autonomous system. It is truly an interdisciplinary topic, very much useful to the electrical engineering students, computer engineering and mechanical engineering students who want to make their future in the robotic systems kind of area. And I'm all thankful to Dr. Yong Wong for sparing his valuable time with us, and also thankful to all the participants to be here till the end and attending this particular webinar. And I'm sure all of you have some takeaway from this particular lecture. And at the end, the video which you have shown about Binghamton University, it is truly motivating, and many of the participants and the students would like to join Binghamton University after their graduation at Navrashna University.
We would love that. Thank you, Dr.
And at this moment, I also would like to thank Provost Dr. Nilay Yagnik and Dean Dr. Sri Hari for supporting this event. And I'm also thankful to Professor Michael Testani and his team for spreading awareness about this joint webinar series in India and the US. So overall, thank you all for being here with us. And the next session or the next talk, that is the third talk in this joint webinar series, is on 23rd April by Dr. Salma Pirzada from Navratna University. It is on the linear and non-linear modeling on machine learning. So I would be happy to see you all again in that particular talk also. See you and have a good day for the participants in US, and good evening to all the participants in India. Thank you.
Thank you so
Thank you,
much.
Dr. Amrish.
Thank you so much, Amrish sir. So if you are not willing to learn, no one can help you. If you are not determined to learn, no one can stop you. With this thought, I sincerely congratulate all the participants, and we will connect in the future as well in the webinars in this series. Thank you, everyone.
Thank you, Mike. We'll meet again.
Thank you, Provost. Look forward to it. Amrish, Kriti, Dinesh, we'll see you again soon. Have a great evening and enjoy your weekend. Have a wonderful weekend.
Bye.